So, we're going to talk about spectroscopy for AP Chemistry today. Let's jump right in. Okay, so there are two types of spectroscopy that we're going to talk about today. They are photoelectron spectroscopy, which we abbreviate PES, and photoelectron spectroscopy gives us data about ionization energy, both about trends and about applications. And then we have mass spectrometry, which provides atomic or molecular mass data as it ionizes either atoms or molecules or portions of molecules. All right, so this diagram should look really familiar to you. This is our electron configuration diagram. This is the diagram we use when we're writing or drawing electron configurations. And this tells us about the different energy levels of each of the orbitals and suborbitals. So what evidence do we have that this is accurate? How do we know that 4F fills before 5D and fills before 6P? Why do we know that 3D fills after 4S and before 4P? So here's how photoelectron spectroscopy works. We have an atom and we send a beam of X-rays at a particular frequency at that atom. You remember that light frequency is directly proportional to energy. And so we know that the energy of that photon is directly proportional to its frequency, Planck's constant times frequency. And when that happens, it knocks electrons off of the atom. And those electrons have a particular energy. In this case, it's kinetic energy because they're moving. And we know that their energy is equal to mass times velocity squared divided by 2. And that's just our formula for kinetic energy. So we know how much energy we put in the form of a photon. We know how much energy came off in the form of kinetic energy. And so we know that the rest of the energy from the photon, must have gone into the effort of removing that electron from the atom. And so we can say that the ionization energy, the energy it would require to remove that particular electron, is equal to the energy of the photon minus the kinetic energy of the electron as it comes off. So this is what a spectrum looks like. Each peak in a photoelectron spectrum, or a PES spectrum, is relative to the other peaks. This gives us an indication of how many electrons required that amount of energy. So in our diagram here, you can see that the peak on the left is twice as big as the peak on the right. That means there were twice as many electrons that required that amount of energy to remove as there were the electrons that required the smaller amount of energy to remove. While we're here and looking at this spectrum, one thing I want you to notice is that this energy reads from right to left, not left to right. So it's decreasing as we go across. So the highest energy level is closest to the y-axis, and the smaller energy level is farther away from the y-axis. We call this relative intensity, by the way. Okay. So we're looking at a new spectrum, and this spectrum, we have a big gap. There's a peak at near 20 megajoules per mole, and there are two peaks near 0 megajoules per mole. And you notice that the first two peaks are the same size. That tells us that there were the same number of electrons that required that amount of energy. And this third peak is about half that size. There's a big gap in these two peaks, and that is because the second orbital here, which we're going to assume this is a 1s and a 2s, we'll talk about how we know that in a minute, required far less energy. So this, when we see a big gap like this, it tells us that we have had a change in energy levels. And we can see there's these ones that are less strongly held are probably our valence electrons. Well, certainly our valence electrons. Inner orbitals require more energy to remove because they're closer to the nucleus, and the valence orbitals require less energy to remove. When we're looking at this spectrum, so we know that this inner orbital can only be an s, and then the next two orbitals have to be s and p. We know that in our first two peaks, we have twice the height of the third peak. We know that 2 electrons can go in the s orbital, so this tells us that there's only 1 electron in that p orbital. So we know it has to be 1s2, 2s2, 2p1. If there were more internal or inner orbitals, internal electrons, inner electrons, then we would have more peaks here. The fact that we only have the 3 and the 2 that we see, the farther left 2, are the same size, tells us they must both be s. So that's how we know this is 1s2, 2s2, 2p1. Okay, so from all of that, we know that this is the photoelectron spectrum of boron. So a few things about these types of graphs. Sometimes 1s is going to be cut out because it's too far away and it makes the graph too long. Other times that scale will be truncated, so you'll see a little 2 lines and a little gap in between, and that allows the graph maker to put 1s on, even though it would normally be too far away. And so you'll notice that the scale is not consistent across the graph. Ionization energy is always talking about removing electrons. Photoelectron spectroscopy measures the energy required to move not just one, but all of the electrons. They're removed from the outside to the inside. The ones on the outside require the least energy to remove. The ones on the inside require the most energy to remove. Occasionally, they'll flip the scale and the lower energy will be first, so just pay attention to the scale. So here we have another diagram. This one illustrates what I was talking about with the truncated scale. So here we have 2 peaks that are the same size, and then we have a third peak, and this third peak is much larger than these other 2 peaks. In fact, I would say it's 3 times as large as these 2 peaks. And then we have a fourth peak, which is smaller than either of the first 2 peaks. So knowing what we know about elements and orbitals, we're going to say that this is an s orbital with 2 electrons. This is an s orbital with 2 electrons. This is a p orbital with 6 electrons. And this next one is going to be another s orbital, but it only has 1 electron in it. So this element would be 1s2, 2s2, 2p6, 3s1. So we know that it's sodium. All right, there's some resources for you guys. All right, and let's look at some sample questions. So we have 2 photoelectron spectra here. They show the energy required in both cases to remove a 1s electron. So they're telling us in this case that we're removing the 1s. It's asking us to say which statement best accounts for the fact that the peak in the nitrogen spectrum is to the right of the peak in the oxygen spectrum. So let's take a look at our scale. We know that to the right in this particular scale means less binding energy. Okay, so a lower ionization energy for this 1s electron than for this 1s electron. How would we explain that there's a lower energy to remove this 1s than this 1s? Well, let's think about what we know about nitrogen and oxygen. Nitrogen has 7 protons, oxygen has 8 protons. Nitrogen has the same amount of shielding as oxygen because they're in the same period. So that means that there's a greater effective nuclear charge for for oxygen than there is for nitrogen. So let's see what we can find in terms of our multiple choice questions. Nitrogen atoms have a half-filled p subshell. Well, that's true, but is it relevant? There are more electron-electron repulsions in oxygen atoms than nitrogen atoms. Also true, but that would decrease ionization energy, not increase it. The electrons in the p subshell of oxygen atoms provide more shielding than electrons in the p subshell of nitrogen atoms. Also true, but it's a small contributor. And then D says nitrogen atoms have a smaller nuclear charge than oxygen atoms. That is true, and that would contribute to a lower ionization energy, and so the answer that we're looking for is D. Okay, another photoelectron spectrum. We don't know what element this is, but we see a peak here, a peak here. Okay, each of those have the same number of electrons. We see a larger peak. So at this point, we're starting to think, okay, 1s, 2s, 2p. This peak has the same size as peak A and B, so that's going to be another s orbital. And then we have E. Now, it's the same size as A, B, and D, but we know at this point, 1s, 2s, whoops, 2p, 3s, this must therefore be a 3p. So which peaks are representative of the binding energy of p orbital electrons? C and E. A, B, and D are s orbitals. Okay, one more, right? So here we have another photoelectron spectrum. And again, we have 3 peaks of the same size. So we assume 1s, 2s, that would be 3s. This would be 2p. This would be 3p. Now we've got to look at sizes. So we know we're looking for 1s1, 2s2, 2p6 because it's 3 times as big, 3s1, 3p, all right, sorry, 3s2, and 3p, it's bigger than the 2, smaller than the 6, so we're looking for a 3 here. So B is our size. If this were 3p5, this peak would be all the way up to here. Okay, last photoelectron spectrum. So this is nitrogen. Asks us, which of the following best explains how this spectrum is consistent with the electron shell model of the atom? So does our leftmost peak represent valence electrons? No, our leftmost peak represents inner electrons. The 2 peaks at the right represent a total of 3 electrons. Well, no, that's 2, and this one is 3, so that would be 5. The electrons at the 1s sublevel have the smallest binding energy. No, they have the largest binding energy. The electrons in the 2p level, here they are, have the smallest binding energy. Yes, that part is true. All right, second type of spectrometry that we're going to talk about, or spectroscopy, is mass spectroscopy. So it gives us the mass to charge ratio. That's what it actually measures, and it allows us to determine the mass of unknowns. It also allows us to determine the mass of isotopes and to find the relative abundance of those isotopes. Here's how it works. We actually ionize our sample, send it through a beam of electrons in order to charge it, and then we accelerate that beam. Now we have these charged particles and we send them through a magnet. That magnet is going to cause those charged particles to bend, to change their path. If they are heavier, they bend less. If they are lighter, they bend more, and so that allows us to separate them by their size when they hit the detector at the end. So you can think of this as, this is all about inertia. So you guys know if you're driving a car and it's a heavier car, it requires a wider turning radius. Lighter cars require smaller turning radius. Same thing for our charged particles here. So this is what a spectrum looks like out of a mass spectrometer. The relative height of the peaks tells us the relative number of either particles or atoms that have that particular mass. Across the bottom, you'll see two different types of scales. You'll see one like this that says mass per electron, or this is a mass to charge ratio. You will also see it simply labeled mass. Sometimes that calculation has been done for you, sometimes it hasn't. So we see that we have different heights of peaks and different masses across the bottom. Here's the mass spectrum of copper as we take a sample from nature. So we know this is pure copper, and we see that we have two different peaks. We have a peak at 63 and a peak at 65. And we see that the peak at 63 is much taller than the peak at 65 because there's much more copper 63 than copper 65. So this sort of information allows us to determine isotopic abundance. So some sample questions. So this one asks us to take our knowledge of the periodic table, which you of course would have a periodic table available to you. And it tells us that these two elements, iodine and tellurium, have similar average atomic masses. So this mixture was believed to be iodine and tellurium, and it was run through a mass spectrometer, resulting in this data. So when we ran it through the mass spectrometer, we got several different values for masses. Now, this question stem tells us all of the following statements are true, but which one gives us the best basis for concluding that the sample was pure tellurium? So the first one says tellurium forms ions with a -2 charge, whereas iodine forms ions with a -1 charge. Well, charge, and even though we're charging them, does not have anything to do with mass spec. Tellurium is more abundant than iodine in the universe. That's irrelevant to our sample. Iodine consists of only one naturally occurring isotope with 74 neutrons, whereas tellurium has more than one isotope. That one is going to tell us that there's no iodine here. And iodine has a higher first ionization energy than tellurium does. Again, true, but irrelevant to the question about mass spectroscopy. Okay, so now we have this unknown atom, and it tells us, asks us questions about this spectrum. So it says, which of the following statements is false? Peak A and peak D come from atoms that have the same number of electrons. Well, if it's all from the same atom, then they all have the same number of electrons. So that's true. There are 7 isotopes of atom Y. So if we count 1, 2, 3, 4, 5, 6, 7, well, that's true. Peak C comes from the most abundant isotope of Y. Also true, this is the tallest peak. And peak D comes from an atom with 4 more protons than the atom that gave peak B. Well, if it had more protons, it would be a different atom. It does have 4 more of something because we have a mass of 96 and a mass of 100. But when we think about isotopes, we know that their difference is not in number of protons, but in number of neutrons. Okay, one last question. Mass spectrum of the element is most likely represented by which of the following? So we're going to find our periodic table, and we're going to look up that element. There we go. And it tells us its average atomic mass is 121.76. So probably not this, because then we would have a mass of 122. And it's close to 122, but it's not exactly 122. This would give us a mass close to 124. This would give us a mass higher than 122. This is going to give us a mass close to 122, but smaller than 122. So it's going to be B. Okay, as always, if you have questions, please let me know.